I'll send you.
Today is about programming in Ruby type theory. So when we left our heroes, we were doing this example here, right? We had the European style database, European style dates in the database. So we had, 35, 1956. We were trying to convert that to the American style dates, 5/30, 1956. And last time, we went through and used inductive recursive universes to build a generic program. We implemented map. And then we wrote the function that converts one to the other and proved that it was a bijection using the embedded domain-specific language of inductive recursively defined functors, blah, 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 that we defined last time, right? So we went through all that work to code up the technology that made this program easy to write. And then this program looked like, when we wrote it, right. This program looked like the thing on the left, right, which said, how do we write this program and prove that it's a bijection? Well, first, we define the swap function, so swap of xy equals yx. Then we prove that swap is a bijection, where the type of bijections is tuples of a function from here to there, a function back, and then two proofs that it's the identity in both directions. Okay? And then we defined a functor saying the spot in the data structure where we want to hit it with the transformation, right, which says inside this list of tuples of keys and names and the point where we want to hit with the function and natural numbers, we're going to apply a function, right? And then we defined the conversion function that flips around the month day inside the data structure by saying map there and apply the swap function. And then we proved that the swap function was a bijection by saying, the conversion function between the two databases was a bijection by saying it's defined by map, and map is always a bijection. Because in lab yesterday, right, did people look at the task that said prove that map is a bijection? Some people? Cool. OK, so there's a task in lab that proves that that generic program map is always a bijection when it's given a bijection. Okay, so it preserves bijections. So any questions about the code on the left from yesterday? I know it was a long time ago, and there's been a few lectures since then. OK. And then the big reveal at the end of yesterday was that the homotopy type theory version of this code is essentially the same. We define the swap function in the same way. We prove that swap is a bijection in the same way, except here in the, so if you go grab the code for today, there's a preliminaries HOTT file, and bijection is actually defined there. And we define bijection with what's called a record type rather than defining it to be a sigma. So instead of writing out sigma this, sigma that, sigma the other thing, you can define a record type which has named fields. And is bijection is just the constructor for that record type. So these are the same components as over there, but they're packaged together a little bit differently. Okay. And then we define there, which is just a regular old set arrow set function, right? It's just the function that, given any set, computes the set list of nat cross string cross a cross nat. And then the rest of the code is basically the same in the sense that convert is defined to say transport there UA of swap. And I'll need to explain to you what transport and UA are. And convert is a bijection is the same proof as before, except here we say that transport is always a bijection instead of saying that map is a bijection. OK, so questions about that bit of it or how the two line up? OK. So what I want to do now is go through, oh, yeah.
On the right, you've got there A, sort of
Yep.
there a big A. On the left, there's just this free big X.
Yes.
Can you remind us about that?
So the functor library that we defined yesterday had functor combinators for lists and constant functors. So list is the lowercase list. Constant functor is the capital K. X is the one variable in the functor. So the interpretation of that is that type constructor. Yeah. OK? OK, good. All right, so what I want to do so you had a chance to play with the functor library a little bit in lab yesterday. So hopefully if we run through how convert runs, it won't be so bad, because this is like over on this side. We can say, what happens when I run convert? And then I'll switch gears and tell you what happens when I run transport. And without spoiling too much of what's going to happen, transport is going to run exactly like the map function that we wrote yesterday runs. So let's just go through that. So if we step through the evaluation of map there swap f, okay? So we're saying for the, let's see, is there on the screen? Yeah, so there up there is the functor that's list of stuff, right? So if you think about how the map function that we wrote yesterday runs, when you map list the list functor, what that turns into is list.map in the second line here on the recursive call map there one swap, right? Because we defined map for list to be list.map. So here I'm writing an equation chain. You might have looked at the problem in lab where we asked you to do an equation chain. So you can read this as just sort of a chain of equality steps. So map there swap is equal to the next line is equal to the third line is equal to the fourth line, dot, 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 all the way down. And then over in the right, you write the reason why those things are equal. And in this case, the reason is reflexivity. And the reason is reflexivity is just that that's literally the definition of map, right? Map on the list functor computes to list.map. Okay? What does map, so if we look at the recursive call, it's on map there one, right? Where there one is the same functor, but I peeled off the list because I already processed the list bit of it, and I'm left with whatever's inside of list. Good? Okay. So what is map at there one? Well, the outer connective of there one is, because products are implicitly right associative, it's that first product, that first knat cross stuff, right? So Ian, can you, yeah, there, right? So that's the outer connective there. And you remember from the map library from yesterday what map at products does. Yes? Map at products applies map recursively to the two sides of the tuple. Okay? So what this the next step that this function takes is to list.map of a function. And when that function is given a key k and a rest, I called it r, so like the whole rest of the record, it maps knat on the first part and with there2 on the second part, where there2 is just the same functor, except now I peeled off of the knat. Okay? So if you look at the case for map of cross u, that's exactly the computation step that it takes. Good? Okay. Where do we go next? So next, let's evaluate the map knat swap f k. So what does map do for a constant functor? Well, map at a constant functor is the identity function. Got it right this time. Okay? Right? So map at constant doesn't apply the function at all. Right? Map at a constant functor just says, I'm the identity function, so I leave k unchanged. And so in the next line, we're left with map at there2 swap f r. Okay? And if we look at there2 up there, you'll see that it's a couple of products and a couple of constants. Right? So the thing that's left to do in there2 is k-string cross x cross knat. And when we have a couple of products and a couple of constants, I've now skipped a few steps and said, at products, we apply to each component. At constant, it goes away. So where we get is that if you give me kn month, day, year, then I'll give you back kn map x swap f month, day, year. And that's just applying. So if you understood how to get from the second line to the third line and the third line to the fourth line, this is just applying those steps again a couple of times. Right? For products, push in. For constants, cancel. Okay? So now what we've got is map at x of swap f on month day. Okay. What does map at x do? Map at the identity functor applies the function it's given. In this case, the function it's given is the swap function. So it applies the swap function to the month day. And the swap function, remember, was defined by saying, take that, return that. And so we get the code that you might have written by hand if you weren't using this functor library, which says list.map of give me this database record, and I'll return this database record with these two things swapped. Okay? So any questions about how map evaluates by recursion on the functor in this example? Okay. So if we go back to the split screen, then over here, I've written the same program in homotopy type theory. And what I'm going to do now is show you how that program evaluates. Okay? And it's going to evaluate with exactly the same series of steps that I just showed you in the code that we wrote yesterday. So the first thing I need to do is explain transport. And have we talked about transport yet? No. OK. So let's actually just implement transport. Doesn't really matter where. OK, so let's call it transport prime, because transport's actually in preliminaries.agda. But if we ignore the homotopy stuff for a minute and just think about transport. So transport is going to say, give me any type A. Well, yeah, A colon set, good. Give me any two, what order do I want to do this in? Give me any other type, let's call it C, okay, where C is not a type outright, but it's a family of types indexed by A. So C will take A to set. And let's make C an explicit argument, just because when you call transport, you basically always need to provide C. Okay? And now let's take A1 and A2 in A, little a1 and little a2 of type A. And we can actually make those implicit. And now let's take a proof P that A1 equals A2. And what transport will do is it will say, if you know that A1 equals A2, then we'll get a coercion function from C of A1 to C of A2. From C of A1, so capital C applied to little a1, to capital C, so a function that takes that to, OK, so let's write a function. Sorry, I don't have this code for Ian. That takes C of A1 and returns C of little a2. OK? All right, so now let's just put in a transport prime of CP equals, or CPX equals question mark. OK, and if we didn't screw it up, we can load. Yeah, is this the top of the file? No. Oh, we're not indented properly. Yeah, sorry. OK, great. OK, so what is transport? Does it remind you of anything from Amal's lectures? Looks a little bit like. Yeah. Not quite, but I OK, it does look like the elimination principle for equality. What I had in mind from Amal's lecture was transport looks a little bit, if you squint, like contextual equivalence. Okay? It looks like what it's saying is, give me any context C. And if A1 and A2 are equal, then they're interchangeable in all contexts, right? So like if you define equivalence to be contextual equivalence, you have for free the principle that equal things are interchangeable in all contexts. So here what we're saying is, give me any context C, and if A1 and A2 are equal, then C of A1 and C of A2 are equal. Now, we're not quite asserting that C of A1 and C of A2 are equal yet. We're just asserting that I can get from C of A1 to C of A2. Okay? But it's the same kind of idea. And the other difference is that this kind of context is not a function into bool or a closed term of type bool with a free variable or something like that. It's a function into type. So it's a different notion of context. But it's the same kind of idea. It's saying, if we know that A1 equals A2, then we can always replace A1 with A2. OK. How do you want to prove this?
Case.
On?
P.
OK. So let's make case on P. Good. Now what do we have to do? We just have to, we have a C of A2, and we have to come up with a C of A2. So let's just return X. OK. So that was easy. It's easy to see by dependent pattern matching that you can always replace equals with equals, because propositional equality is defined to be a type with one constructor reflexivity. Match on it, and then you get this. Okay? Now, what does this do operationally? How would you run this program? You're given a C, you're given a P, you're given an X. What do you do?
I mean, in a sense, you're traversing the structure of the family and performing the.
Not yet.
Okay.
We will.
Not yet?
Yeah,
Okay.
I mean, you're foreshadowing. But it does nothing. But at least if you don't distinguish equality from every other inductive family, right? So like, if reflexivity is just a constructor. It's the same as HBH node or HBH empty or tree or node or empty or anything like that, right? So this is just a pattern match. And what you do with a pattern match is you run the thing, wait for it to turn into a constructor, and then reduce. So the way you would run this is you run the proof P until that proof P computes to reflexivity, right? Just like you would run a tree until it computes to empty or node. When it does that, you reduce by saying, oh, I told you what refl goes to. It goes to X. So when the proof turns into reflexivity, transport vanishes. Okay? So this is actually how Agda runs transport. Run the proof, compute reflexivity, then vanish. Okay? And the reason I wanted to point this out is that it's really important for homotopy type theory purposes that this is not how we run transport. So what I'm going to show you is an alternate way of thinking about transport that gets us this generic programming, this functor library, to come out. Okay? So there are ways to mimic homotopy type theory in Agda, but what I'm going to show you today is sort of what homotopy type theory really should be. And there are ways to fake that in Agda, but it requires kind of switching how we think about transport. Okay? So let me just write the typing rule for transport on the board over here. So transport says if, I'll leave off some of the arguments, but if alpha, or what do we call it up there? We called it P, says that A1 equals A2, and C is a family of types, then transport CP is a function from C of A1 to C of A2. Okay? Yeah, we're going to raise the screen, I guess, now. OK. The screen will come back down in a bit, don't worry. OK. So the other ingredient, and this is sort of the first new ingredient in homotopy type theory, is something called the univalence axiom, which was written UA in the code. Okay? And that might sound scary. It's like a word that's not exactly English, but that's OK. OK. And UA is actually a very simple principle with pretty deep consequences. Okay? And we've already built up all of the vocabulary we need to say what UA says. What UA says is that if there is a bijection between two types A and B for any AB colon set, then A equals B. Okay? So the new principle that we add in homotopy type theory can be said as bijective types are equal. Whenever you write down a bijection, just like we were doing in the example before, between A and B, you're actually proving that those two types are equal. And the force of proving that two types are equal, right, why is that different? Why is it different to have an equality than it is to have just a bijection, right? We could just program with bijections in Agda like we have been doing. What does this buy us? What this buys us is exactly this principle. When you prove that things are equal, you know that they are interchangeable in all contexts. So before we added univalence, it might have been the case that there's some construction we can do in Agda with one type that we can't do with some bijective type, right? It might not be the case that all constructions respect bijection. Univalence is stipulating all constructions respect bijection, because by univalence, bijective types are equal. By transport, equal things are interchangeable in all contexts. So it's a very strong statement to make. The reason it makes sense is that it is in fact true that everything you can do in Agda respects bijection. So we can kind of add this as a principle to say, not only is it the case that everything already there respects bijection, but we're going to insist that everything you ever add to Agda respects bijection. Okay? And out of that, you get some generic programs, some principles that you get to program with. So let's do an example. Let's do the convert example. So remember that there of A was defined to be list of nat cross string cross A cross nat, and convert of, which took a database to a database, was defined to be transport at there of univalence axiom applied to swap, full stop. Okay? So why does this have type database arrow database? Let's type check this. Swap, what was the type of swap? Swap was a bijection between nat cross nat and nat cross nat. Okay? Good? Univalence applied to swap then says, hey, because of that, nat cross nat is equal, in the double equal sense, to nat cross nat, right? But something really new and interesting is happening, which is this proof of equality between nat cross nat and nat cross nat is not reflexivity. This is a different way of showing that these two types are equal than reflexivity. It's taking this swap function And somehow, when you take the swap function and turn it into an equality, you're still preserving the fact that it behaves differently than reflexivity. So what we have is what you might call computationally relevant proofs of equality. So if you thought that equality had no content, it was just a mere proposition, it was just kind of a fact, not true anymore. Equality can have real computational content. And this is what this example shows. So we take this bijection, okay? Now what does transport there do? When we apply transport there, the whole thing has type there of nat cross nat, arrow there of nat cross nat. And if you do the substitution, you'll see that when I plug in nat cross nat into there, I get the type of databases, right? Because I plug in nat cross nat for A, which gives me my key, name, month, day, year. Good? OK. So how does this run? Well, we've already implemented how this runs. It runs just like in the functor library from yesterday. But let's trace through it. So if I call transport there of UA swap in homotopy type theory, we're going to run transport very differently than we run transport in Agda. Okay? We're not going to run transport by taking this proof, running it until it hits reflexivity, and then disappearing. Okay? Why not? Because this proof doesn't run to reflexivity. It's a different canonical form, like it's a different way of making a bijection between nat cross nat and nat cross nat. It's not even equal to reflexivity. So we can't run it until it turns into reflexivity, because it's never going to do that. So you can think of univalence as adding a new introduction form for equality. And what I'm going to try to suggest to you is a little bit of why it makes sense to add new introduction forms for equality, right? Because if we think of equality as an inductive family, it's generated by reflexivity, then it's a bit weird to say, we're going to toss some other stuff in too, okay? But in fact, we can toss some other stuff in too. And the reason is that, well, you have to switch your, you have to switch how you think about transport. And then because of that, we'll figure out how to make sense of it. So what I'm telling you about here is all work in progress. For some special cases of homotopy type theory, we know how to make this kind of computational notion work. But in general, it's a really hard problem for reasons that I'll get to later. So just keep in mind that this is current research. But for this case, I can tell you what it does. Okay. So what do we do when we transport their UA swap? Instead of running the equality proof down to reflexivity and vanishing, we start looking at the context in which we said we would like to apply transport. We look at there. What's the outer type constructor of there? List. And we'll have a rule that says if I transport and the, If I transport and the outer type constructor is list, then that turns into list.map of transport at what I'll call var2 of UA swap, close, close. Okay. And what is var2? Well, var2 of A is just I take there and I peel off list. So it's whatever's left inside of list, which is in this case nat cross string cross a cross nat. What? Oop, sorry, skipped a step. There one, yeah. Okay. There one. All right, so this is exactly the step that you understood back in the implemented functor library. When I'm running map at list, it turns into list.map, and then I map the recursive call. Yeah?
So UA has changed type here.
Nope, UA is still concluding that nat cross nat equals nat cross nat. So swap still has, swap is still a bijection between nat cross nat and nat cross nat. And this is still a proof that nat cross nat equals nat cross nat. And if I take nat cross nat and plug it into there one, I get the tuple sitting inside the database. Good? OK, so what do we do next?
Well, you think of transport here as dispatching off the there.
Yep, you should think of transport as dispatching.
It's kind of ignoring the UA swap bit.
Ignore the UA swap, dispatch on the there. Yeah.
Wait, so how does transport, find what list.map is? And where does it come from?
So basically, list.map is sort of in a fundamental way associated with list, right? So just like when we did it for the functor library, we told in the implementation of map for the functor library, we said that map at list is list.map. That's sort of built into the operational semantics of homotopy type theory. So list.map kind of plays a fundamental role.
So you're trying to do that for whatever type.
Yeah, exactly. Because the whole idea is that when you combine this with this, one thing that happens is every function from sets to sets becomes a functor. Okay? Which means that in the operational semantics, there is functoriality built in. Okay? Yeah.
What about converting?
Yep, we'll get there. Yeah. OK, so what next, just to finish this off? What do I do when the outer constructor is a product? Yeah, push inside to the two components, or the breaststroke, apparently. OK, so lambda, give me a k and r, and I will do transport at lambda underscore dot nat on k, because that's the first component, and then transport at lambda, or let me name this there two. So let's just define there two of a equals string cross a cross nat. OK, and then we'll transport at there two with, oh, I forgot UA swap on the other side, sorry. UA swap on R. And here, I also wanted to write UA swap. List.map, close. OK, good. OK, does that make sense? So remember what map did for pairs. It pushed inside. OK. Transport for pairs pushes inside. You get a transport on the first component and a transport on the second component. OK, good? OK. All right, next one. Now what we have in the first component at transport of lambda underscore dot nat. Lambda underscore dot nat is a constant functor, just like knat was when we did this in the embedded domain-specific language. Okay? So what do constant functors do? They vanish. So we get list.map of lambda kr goes to k, and then transport there two of UA swap on R. Okay? And that's just because transport is dispatching on the type family. The type family in this case is a constant 1. And when you have a constant 1, the transport vanishes. Okay? Good? Remember this one from before? Yeah. Okay. Now what? Well, before, when we did this, I cheated a little bit. I'm going to do the same cheat here too, right? We talked about how you run transport for products. We talked about how you run transport for constants, right? And so if I do this step and this step a couple more times, right? Do the one for constants, do the one for products, then what I get is list.map of lambda key name month, day, year goes to key name transport lambda x dot x. Here, let me push it up. UA swap on month, comma, day, comma, year. Close, close. Okay? So if I push inside the pairs 2 more times, and then I cancel the constants 2 more times, I say, leave the key the same, leave the name the same, leave the year the same, and end up with this. Okay? Good? So now the only thing left to do is to check that, I'll just write it again, transport lambda x dot x on UA of swap on month, day actually steps to day and month. Okay?